Hello, everybody. Today is May 16th, 2023. I am Justin Hickman with Vertispan, and today I'm going to be continuing where we left off last time with re-implementing B trees using B plus trees. Since the time that we were here, I made a couple of changes, and I'm just going to introduce those real quick. I made a couple of commits to my branch, actually just one, and some local modifications. But the very first change that I did was basically to remove kextends comparable. So now the key doesn't have to extend comparable. That way you can create whatever class that you want. But the thing is we will definitely need to be able to detect some sort of comparator if you don't provide a custom comparator. So notice that if you just create a B tree with the number of degrees, it's going to go to the constructor, passing out a null constructor, which in there will basically just make a determination. And I'll probably change this up at some point, but this one, I'm basically just holding on to the raw type comparator. And the very first time that we call compare, I'll just check to see if one of the instances is comparable. Of course, that's going to be a problem if it's comparing null to null. So that might be problematic. I don't know what to do with that one yet, but I wanted to be able to at least have the natural order, basically utilizing the fact that the objects in the B tree might actually implement the comparable interface. Otherwise, you just specify your own comparator outside of there. So that just required me to, where's that window? There it is. Just going through all of the different types and making sure that they all had the extends comparable removed off of the key. This one I actually updated to escape the key. Because I was just playing around with some of the keys that were a little bit more complex, and I just needed to make sure that certain characters were escaped in the GraphViz exporter. And that one looks pretty simple, just removing the comparable. So that actually makes it a little bit easier, where you can actually have a B tree of any key and any value. And that was the other thing that I made local modifications for. Just haven't committed it yet, to be able to apply a value to the B tree, because I mean, it's nice to have the keys auto sorted and fast lookup, but we need to actually associate some sort of data to those nodes. So in that particular case, my camera's in the way, but we can see that I added the generics for the value side, and I updated the add method so that I can just delegate being able to add. I might change this later to be like insert or set or put, basically more map like, to be able to set the key value pair. And that goes all the way through down to the internal node. I think I just basically rearranged the other code. I didn't rewrite anything. It looks like I just rearranged, alphabetized all of the other methods, changed the visibility on some of these. But otherwise, with the add method, let me find that, we can see that I'm maintaining a values collection, which is going to be parallel to the keys collection. And because keys is in the super class, I wasn't able to convert that to a map or anything, so it probably just makes sense to do it this way. So any operations for mutating the keys, such as inserting or deleting keys, I need to do the same sort of thing on the other values. So you can see that I added this dot values add down here, and then it's also just removing and so on. So that makes it a lot easier for me to associate values. So in today's stream, I actually want to start looking at searching abilities, because I mean, what's the point of holding this B tree or B plus tree data structure if we can't actually search it and do something useful with it? So I am going to first look at my unit test just to make sure that it all passes. I don't know if I have updated anything in the unit test since the last time we streamed. But basically I have the add data. I think I added labels since the last time. That way we have some information in the test runner, so we can actually see what the intent was, like overflow splitting, large key set. So if any one of these fail, I would at least be able to see the data structure of the arguments that was used to generate that unit test. Didn't do the same on the remove, but I think for the most part, all of this is at least working. Tested a lot of different cases for removing, and I think I got it all working now. So whenever it generates this unit test, I can see all of these different graphs, and it doesn't. Let's see. Let me just grab the very last one. So if I just copy that one, and the nice thing about this test runner, because of the fact that I'm just debugging every single one of these, I can just click on this, and it'll show me the system out just for that one test, and I can easily copy and paste for that one test. And then going over to Chrome online viewer. I don't remember which one I used. That one looks fine. There we go. Yeah, that one looks fine. So that is what the test output looked like, and I think I'm just outputting the expected output. I can't recall which side I'm going with, but this seems to be adding and removing nodes the way that I expected. So today we're actually going to be looking at the ability to traverse these nodes. I'm not entirely sure how we're going to accomplish that, but let me go ahead and commit these changes before we actually start modifying the stuff here. So this is adding an associated value to the B plus tree. I think that's essentially all I did. Yeah, so let's go ahead and commit that. There we go. So we should be able to start testing search capabilities. So I am going to collapse all of these. Yeah, whenever you're using a parameterized tests, kind of makes everything a little bit more chaotic in your unit test file. The non-comparable one, this is something new, and this is basically whenever I was doing a comparison of a key that was non-comparable, meaning I didn't implement the comparable interface. And that test is test comparable. There we go. So here I'm just asserting that this throws a illegal argument exception. So then whenever I try to add two, and I had to add two because the compare isn't actually called until you actually have two to compare. So then I just make sure that it throws the illegal argument exception whenever I construct a B tree with a non-comparable key. But here, another test with the non-comparable, but I'm using a comparator as the constructor arg. And then whenever I add two items in this, it doesn't actually throw an exception because it will use whatever comparator that I have provided it. So that's pretty nice. It will increase our chances of being able to do really cool things on this because of the fact that we're not bound to any type that implements a comparable. We won't have to, for example, wrap all of our types in case you don't have access to the source code of the beans that you're storing. You don't have to actually wrap them just to implement the comparable interface. So let's start testing the ability to search. And I think for the most part, there might be a couple of ways to do this. I know that whenever I was first implementing this, I created two search methods. One, search, and that's more like a contains. I'll probably rename that just to see if it contains that key. Yeah, that might be beneficial. So let's go ahead and test the contains, and I'm going to probably rename that. Key, contains key. What is the map interface? New hash map. Contains key. Yeah, contains key is probably good. And that probably also means that I'll need to update all of these. And just a quick glance to make sure that it changed all of my classes. My face was in the way again. Yeah, contains key. Leaf node contains key. Yeah, I think that's a little bit cleaner because we may eventually do like a contains value. I don't know how close it is to what we want on a like a map implementation. I mean, it's possible that we could go with entirely a map implementation because that's all a B tree is at this point, because I wanted to make sure that it didn't modify any existing value. So if I go to the leaf node and we call add, oh, I guess it was a to-do that I added. Wasn't entirely sure what to do if it was a non-unique key. So in this if statement, it basically just checks to see if the key is not the same as the key that we're passing in at the location that it's providing us. Because if it is, so we would have like an else here, we would probably have to die, or instead of calling add, we would have to call set. So that would change the value at that location. I am not positive because in a map, put that will return the previous value, right? Yeah, I could do that, except for the fact that the add here, it returns a node only if it had to split. So pros and cons, I don't know what to do with that. But since this is going to be an internal usage for now, not making it an external use for this B tree implementation, it's probably fine just to leave it as is. We could just set the value. overwrite it, or we can throw an exception. We'll just have to find out once we get to that point. But let's go ahead and test the other contains. So a new B tree of integer and string. And 5 degrees is fine. Tree dot add and integer 5. Let's just go by tens, shall we? There we go. And we can just debug that tree for the other time being. So let's go to this debugger. Let's run that. There we go. Here's the other contains. Is there a way to just grab all of this? There we go. So that's what all of the tens look like. I guess I could have done less than or equal to 100. That way we have the 100 in there as well. But yeah, that'll work. Insert true. Tree contains key. I can probably just do it this way. Just do the exact same loop after it added it. I want to do these as separate loops because I don't want to just check the contains right after the add, because that to me doesn't make a lot of sense. But I can do a contains key there. And then I can, for int I equals 9, I is less than or equal to 100, I plus equals 10. So this is going to be 9, 19, and so on. So I just need to assert false. Tree contains key I. That's basically going to say, hey, none of these keys exist, right? So let's go ahead and run that test. And that was successful. Of course, I already implemented this, but let's go ahead and take a look at, let's look at the implementation. Why can't I grab that drag handle? All right, so the B tree will basically just delegate all of the calls to the other root node, which makes a lot of sense. So it's just gonna ask the other root, does this contain a key? And for that one, that's going to be an internal root, because this is an internal root, and that's just going to get the location for that key. Basically, which path should it go down? Should it look at the key here? Should it actually, with internal nodes, we always want to traverse to the other children, and the children can be other internal nodes or leaf nodes, but that's fine. So internal, it'll basically just grab that child at the location and check to see if it has a key. And I am going to go down to the leaf node, and this is basically just making sure that the location is not equal to the key count. Could it be higher? Doesn't look like it. And the keys are equal. So the keys at that location is equal to the key that we're passing in. And of course that does require the comparator to return a 0. And that basically just lets me know that it does contain that key or it does not contain that key. Pretty simple. All right, so now let's grab a range. So I'm going to copy this stuff, and let's Let's grab a range, tree, search range. And this is the start and end. So let's look at all of the, because we're adding 10 through 100. Graph viz tree. Let's just run this one test instead of running the entire suite. This will make it a little bit easier. Then paste that, and we'll have the 100 in there as well. Cool. I mean, we can even change this such that it's degree of 2. And let's take a look at what that would look like. Let's look at what that looked like. Yeah, it made a lot of sense there. Why can't I alt tab to my Chrome? Weird. So here it's a, oh. I don't think I've ever tested it with a degree of 2 before, which that's probably going to be problematic because of the fact that it could contain 0 keys at that point. That's no good. I should probably have a minimum. There may have been something on the Wikipedia page for B+ trees that you can't have anything because if you remember, whenever I construct the B tree, I grab the degrees -1, and then that's the max number of nodes, and it has, because of the rules, it has to divide the number of keys by 2, because it has to at least be half full. So 2 is probably not a good idea. Let's rerun that at 3. And this should look a little bit better because this will guarantee at least 1 key in each node. That looks correct to me. 70. Yeah, that looks correct. All right, so in this particular case, I wanted to spread it out like this because whenever we do a search range, I just want to make sure that it has at least a few levels of internal nodes. We have level 0, 1, and 2, and then level 3 is going to have our leaf nodes. So whenever we grab a range, I want to have a set of these. So what I want is probably grab 40 through 70, but instead of specifying 40, I want to try 35 through 75. Oh, thanks for the follow. Inna Seekin 0, welcome to the stream. All right, so there's my range, and I don't know, it's been a while since I implemented this, so I just want to just double check. I am writing a B+ tree, B+ tree. Well, that's the image. Oh, there we go. Oh, yeah, that's the image. Here's the B+ tree. It's basically a data structure for holding indexed data so that it has faster search times. As you can see, the searches, the inserts, and the deletes are big O log of n for the worst case and the average. So it's a very efficient data structure for. This isn't the B+ language. This is Java. This is just a B+ tree for holding onto nodes. It's sort of like a binary tree, but it's a little bit more complicated with all of the characteristics for how you can add and remove nodes. This is essentially what it sort of looks like. That's probably a bad representation. I don't think Java's hard necessarily. I mean, I think Java has its quirks about it, but it's fairly straightforward. And that's one thing about the statically typed language, such as Java. You have a lot of tools, and things like content assist and stuff like that work pretty well. I know that TypeScript does too, but it's at least not a duck type language, sort of like JavaScript, where you can just slap on new properties. You actually have to define the class structure in order to actually use it well. But I've been implementing this B tree, basically creating like a in-browser database using Java. And the thing that I'm working on today is this search range to be able to produce a list of all of the values. Well, yeah. There's a lot of uses for Java. I know that a lot of enterprises tend to stick with Java. A lot of startups will do like React and Angular for their front ends, but I don't know. I think Java still has a home in a lot of companies. It's not one of those hobby languages that you see people raging about. All right, so my search range, I'm basically grabbing the location of the... Am I interested in different languages? Yeah. I haven't in a while, to be honest. Most of the other languages that I learn for programming is languages that run on the JVM, such as Groovy and Scala and stuff like that. I haven't really ventured too far away from that. My career started with Perl programming, to be honest. Love Perl. At least I did back in the late 90s. Haven't really used it in quite a while. Never been a fan of Python. I know that a lot of things use Python. Lua is pretty good. That one's good for programming like scripts and stuff for like games. A lot of game engines will actually use Lua for their plugin systems. This one's a pretty simple one to get started with. Roblox is using it. Yeah, that's probably true. I know that even in Minecraft, if you ever used Computercraft, Craft CC. Nope, that's not it. Tweaked CC, there it is. They rewrote Computercraft, but all of the other turtles and computers in this mod uses Lua for all of its mechanisms. Yeah, it's pretty nice. That's basically where I've used it quite a bit. I was teaching my son how to program using Minecraft. Pretty fun. But I don't really venture too far away from the JVM though. That and browser languages like JavaScript, TypeScript. All right, so the search range. This is basically just creating an array list. And it's calling search range on the root, giving the start and end and the result. So it's basically just self-modifying this. Oh, well, thanks for stopping by. We're here at least a couple of times a week. Search range. So it's mutating this list and then it's returning that list. Let's take a look at the internal node first. That's grabbing the location of the start. And it grabs the children at that start and just basically delegates through until it finds a leaf node. So let's look at what it does with a leaf node. All right, so this is going to get the other location of the start, and while the location is less than the key count and the keys at that location is less than the end, should probably just I could probably double check in the other root class, because it's going to be it's going to be problematic. Maybe not. We'll have to look at that. So for each one of those, it's going to add the key at that location to the result. And then it's going to increment the location. It's going to check to see if there's a next. And if you remember, this is a double linked list, which I don't know if I needed to implement it as a double linked list. I might remove that. I don't know. It really depends on if we want to be able to do like streams instead of this, where it's just iterating through. I could do it as a stream. Being able to go forward and backwards on the other stream. Let's take a look at that again. So basically it's checking to see if next is not null. If it's not null, it's going to be able to get to the next node. And that's one of the reasons why I switched to a B+ tree, is because of the ability to have this double link list at the end. It does sacrifice having to repeat keys in here, but I also don't have to do a bunch of searches in order to accomplish this. So if the next is not null and the location is key count, meaning that we're at the end of our current node. And that only works because we're doing the location increment inside of the while loop. So then I set the location to 0, which is going to be the first location of the next leaf. So then I grab the next leaf, and seems kind of weird, but I guess that is accurate. So then it just delegates to the next node, being able to search it, giving the start and the end. Well, that actually might work. So let's system out that range. And this is just the range of keys. This isn't returning the values. I'll probably need to modify this to return a tuple instead. That is empty. Why is that empty? All right, let's debug this a little bit. Yeah, that is empty. Why is that empty? Well, let's go ahead and throw a breakpoint in here. And let's just see what we're doing. So the start and the end are going to be 3575. 35. So and this keys. What? Did I accidentally do something? The keys is 30. $35. So I'm going to go here. Yeah, that makes sense. So whenever I'm searching for 35, it's going to go down here. It's going to say 35 is greater than 30. It's going to go down here. 35 is less than 40. So then it's going to go down here. So this is the node that we're currently on. And the index of the location is probably going to be 1. Yep. So the location is 1. All right. Less than key count. So what is the key count? Get key count. So that's going to be false. It's going to immediately be false. So I guess this was a good example. Actually, let me do a best case scenario first. Instead of doing it the halfways, let me do 30 to 70 where the keys actually exist. And let's just see what this is going to look like. I'm pretty sure that we're going to get a Stack Overflow. Yeah, I'm pretty sure that it's going to be a Stack Overflow. That's not going to end. So I guess I got into an infinite loop here. All right, so what was the problem? Yeah, out of memory. Okay. Thought I was going to get a Stack Overflow, but out of memory makes sense too. Because of the infinite loop, it was just constantly recursively calling. And let's figure out why. So if we come in here, we have 30 and we want to get to 70. So while the location is less than key count, see, that's our first problem. Because on that other example, because of the fact that it was greater than the current one and it was at the very end, it would need to go on to the next node. But the only way to go to the next node is if we had a result that matched the criteria within the current node. So that's the first problem. And I wonder if this should be inclusive. Probably inclusive. Makes sense to have inclusive. So it would contain the other 30. So let's put some breakpoints here, go back to the debugger, and let's run this to see where it goes awry. So let's just double check to see. And we weren't able to actually create the unit tests for this. I know that I have these links here, but I think I just put them in arbitrarily what they were supposed to look like. I don't know if I actually traversed that or not to see if the links were actually there. I could probably do that pretty easily, but actually, graph viz outputter. Next. Yeah, so here it's a leaf node. We grab the next. So it doesn't look like we do the other previous though. So the sibling, if the sibling is not null, handle that node, and then we create a link between That node number and the sibling number? Yeah, node's index of sibling. All right. We're going to have to figure that out. That looks like I did implement that though, but I didn't do previous. I'm not sure why I didn't do that. So the location is 0. The location is less than key count because the key count is 1. And the keys at location 0, which would be 30. It is less than 70, so it will go in here. It'll add that key to the other result. Do the location. Check to see if there's a next. And location is equal to key count. I'm going to reverse those logically. So I want to short circuit it on the location, since that is the moving value here. This is basically saying that we're at the end of the current node, and then we want to see if there's a next node to jump into. I should probably have this on the outside. Yeah, this makes more sense to be on the outside. So let me put this on the outside of that while loop. So here, basically going to, let me stop this. Loop through current node keys and add all that are less than the end key. So once it gets through the current node, then it needs to check the to see should we go into next node. And we're just going to do that automatically, even if the next node has a higher value as its first key than the end. We still need to traverse into that that node. So I'm going to change this so that if the location is the key count, meaning that we've gone through all of them. I mean, that's kind of a weird way to do it. I mean, essentially we want to return if the last key that we look at is greater than or equal to the end. To probably do a less than or equal. Possibly. I am not sure. Because this is non-inclusive with the end, right? I don't know if we should do that or not. Let's come back to that, because right now it's implemented in a way that it's non-inclusive. So then it's going to see if we can go into the next node. We grab the next leaf, and while the next leaf is not null, and next leaf key count is 0. What? Why would we have no keys on the next leaf node? That seems kind of weird, right? I don't think I need to do that. That seems really weird. I wonder why that little bit of code was there. I'm gonna remove that. So if the next leaf is not null, which we already know it's not null, and the next leaf keys at 0. Oh, see, here we're actually checking to see if we can go into the next one. But I don't know if we need to bother because we're already doing that once we get in there. I think we should just delegate. This dot next dot search range start end result. I think that's it. Right? Seems logical. Well, there we go. So here we have 30, 40, 50, and 60. So this is non-inclusive. It's not going to include the last one. I don't know if that's way we should go or not. I don't know. Here I'd like to see if it will work on 35 and 75. And again, this is non-inclusive. Oh, that I need to fix before I can run that. There we go. Let's run that again. Let's see what numbers that we have this time. This time we have 40, 50, 60, and 70 because we went from 35 to 75, and those are all of the keys in between 35 and 75 non-inclusive at the end. So basically it's not sure if I like that or not, but search a range from start inclusive to end exclusive. Is that right? It's been a while since I've looked at math notations for this. I may have that reversed, but I think the parent is exclusive, non-inclusive. All right. Okay. I mean that's gonna work. Again, all what? Through the current node keys and add all that are less than. I don't know why I put all twice. That was weird. All right. Yeah, if I were to do a stream, this would be a little bit different. I wonder if I should do a reverse. What does it look like if I do a reverse number here? So if I did 35 to 75, of course, this will probably just return an empty list because of the fact that it's going to immediately know that the end is less than. Yeah, figure that would be empty. True. Range is empty. I should probably put this in the message here. So the first one's expected arrays as list, and we're expecting 30, 40, 50, and 60. As a list, and this is going to be 40, 50, 60, and 70 with the other range. The other message with this with non-existent keys. And I don't need the SSouts anymore. And I don't need to debug that graph viz. All right, there we go. So now I have the ability to do searches. I don't know. Of course, I need to change this. Probably need to return a tuple. I don't know what to call this. Does the Wikipedia page have anything for this? I think I looked at a different blog and they called it a tuple for returning. I mean, I could just return a map entry. Because that's essentially all it is a map entry. So instead of the other result that way, which is weird. I mean, it does make sense to have it in order. So let me, tuple. I don't know if I'm using that word right. I know that Python uses tuples. Basically, being able to is a lame tuple. What's a lame tuple? Oh, map entry. That's kind of interesting. Over here, let me screenshot that so that you can see it. I didn't see the map entry part because it was blurred. Thought that was part of your username. I know it's a lame tuple. Getting rid of generics is nice, but map has a handle entry constructor now. Really? That seems kind of weird. Yeah, that's very bizarre. Like the map interface? Or are we talking about a specific... Oh, of entry. Entry. No, I don't see any reference to URL. Yeah, I'll just return my own key value pair. I'll just call it's internal right now, so I'll just name it tuple. It'll work, right? So this is going to be of a key and a value. That's true. I don't mind that. Where's my internal node? Or leaf node, I mean. There we go. Oh boy. I don't know. I don't see anything. Oh, it doesn't have it yet. Yeah, okay. That's fine. Since I am writing this specifically for GWT, I'll change this just to have a key value pair. All right. So I'm just going to change the B tree implementation search range. And again, I don't know if this should be exclusive or inclusive. I don't know. This is going to return a tuple of key value. There we go. Oh, wait. New tuple. So now we will need to convert these. In this particular case, I only care about the other values, so I'm just going to stream map these. Tuple get key collect. Because that's all I really care about for that particular unit test. All right, so that worked. Here I'm going to test the other values. Test the other values too. I'm just going to do the same thing as I did up here. Test tree.search range of 30 to 70. And this is going to be a tuple range. And how am I gonna assert the other values on this one? Assert true. Tuple range size equals. Oh, I can just do equals. Expected value is going to be 4. So now I can do int I equals 30. I less than or equal to 60. I plus equals 10. All right, so here assert equals new tuple integer string of I, and then value plus I, right? And that's expected to be equal with the tuple range get at I. Oh, wait. Yeah, I guess that was a bad idea, huh? There we go. That should be equal. Nice. Just for fun, I'm going to system out this tuple. Nope. Tuple range get. See. I'll do that beforehand so that I can see what that tuple is. I guess I should two-string it. Where's my class? Did I not must have closed it. Two-string. Nope. Two-string. Let's just generate with a wizard. It's fine. Key 30, value 30. Key 40, value 40, and so on. Yeah, that is correct. That is nice. Guess I don't need to do that. All right, so now I have the ability to search a range non-inclusive. Should I make it inclusive? I should probably make it inclusive. True. Yeah, that's true. But start to end, right. Yeah, that's what I have right there. Yeah, let's just overload this. I don't know why I'm typing this all out. Way you can have search ranges and stuff and have next start equals end plus 1. What does that mean? Next start equals end. What do you mean by next start? Oh, I see what you're saying. Right. Right. That makes sense. Yeah, that makes a lot of sense. So this will give that ability. So now I just need to change this signature to include a Boolean for the inclusive end. And that's basically right here. This or less than or equal keys get location and I haven't implemented that, but inclusive and that. don't know why I'm doing it this way. My mind's not fast enough. There we go. Yeah, my fingers were a little bit faster than my brain. So does that make sense? So if the key count is less than, or the location is less than the key count, and it's either we're less than and not inclusive and, oops, that's in the wrong place. Or it is an inclusive end and less than or equal. That seems kind of weird. Should short circuit that. So I don't want to call the less than unless it's needed. Yeah, that'll work, right? So then I do the same thing, but I want to pass it true for inclusive end, and this will be 70 inclusive end. Probably should have written that test first. Okay, that'll work. That's some terrible JavaScript or JavaDuck. All right, well that works. I guess I don't really need to worry about the previous. I should probably migrate the previous off of there. I don't think I'm using it for anything. I think I'm only using next, but I could be wrong. I'll have to double check to see if I'm navigating the previous nodes for relinking stuff. All right. That should do it, right? Let me just double check by running the full test. All right, everything passes. I guess we can start looking at the indexes for this stuff. But before I do that, let's go ahead and commit that. All right. All right. So we have the index here. So let's pop over to this index. We're gonna have to completely rewrite this index capability. And honestly, for the GWT-DB stuff, I guess that's the end of the B plus. Well, I guess I did name the stream B plus trees indexing. So we're still doing the indexing stuff. We're just concentrating more on the GWT database side now. So I'm thinking, in regards to the indices, I kind of want, because right now we're using a tree map. I think I want to change this out to a B tree for the main fetching. Because like in this, I don't have the ability to do the other ranges and stuff like that, so I might do that. Final, and I need to change some of this, right? Can't recall where my B tree is. All right, so this is the B plus tree. I'm going to be migrating away from this older B tree implementation. So this is going to be string, because we're using string keys, right? Because my IDs are all strings, and this is going to be of the D object. I'm going to keep it small for now. Eventually this will probably be like 50 or 1,000 or something like that. I don't know. All right, so let's... Yeah, I'm gonna have to re-look at this. So this is a store entry set. So this is basically just going through all of the entries. Yeah, I guess that's one thing that I didn't do is provide a mechanism in the B tree to return all of the objects. Like a get all, something like that. Yeah, so let's implement a get all. I'm going to rename this store to something else so that it doesn't fail. But I do want to change the unit test first. All right, so for this one, tree, get all? I don't know. Oops, I did not mean to do that. And this is going to return a list of tuple of integer string tuple range. All right, so I'm gonna rename that, but I needed that there so I can rename both at the same time. I don't know what I was doing. List of tuple of K to B. Get all. I guess I don't have a last leaf key. That might have been nice to have. I'll have to think about that. It's basically just iterating through all of the last children of all the internal nodes, and then the last key value pair of the leaf node. Yeah, let me do that. Let me return a search range using the root get first key to root get last leaf key. Let's go ahead and implement that. Get first leaf key, protected abstract K, get last leaf key. Go to the internal node first, last, and this is going to return children get children size -1, get last leaf key. Right? I mean, that seems correct. Let's see if it is correct. So basically, we're just grabbing all. And for each one of those, we are going to reconstruct a tuple and just making sure that they're all equal, and that appears to work. All right, cool. So that allows us to get all of them, and it's I guess that's the most appropriate way to do that. Just reusing the exact same implementation there. Yeah, might as well commit this. B tree. Not that one. All right. I'm just going to amend it to the previous commit because it was all somewhat related, right? All right, cool. So let's go back to this guy here. And for each of these, I guess that's going to be a JS object. I could create a convenience for values. So if I had a list of V values, I can return a get all stream map tuple get value that. Right? That's basically grabbing all of the other values. Get all. It's not an entry now, but apparently duck typing, it uses the same methods. So that's fine. We don't have a size. I guess we can implement a size. All right, so now I need to implement size. I guess size doesn't really mean anything at the internal node. That's essentially what size is on the internal node. Just going through all of the other children and asking for their sizes. And then leaf node. Return keys.size. Or yeah, I have to do get key count here. Yeah, it doesn't make sense to do a key count at the higher node because it's only the keys at that position, but it does make sense on the other leaf node just to return that tree count. The key count. Oh. All right, so I am going to made some changes that incompatible now. So before I get to that, I want to go back to my my test here. And this is where we're going to test the other size. All right, so this is going to be 10. All right, let me just add a 0 there. Just to make sure that it expected a wrong number. There we go. Cool. So I'm kind of curious. What does the 100 nodes look like? So I run that with 100 nodes. That's what 100 nodes looks like whenever you're doing a degree of 3. Yeah, that's kind of ridiculous. Holy cow. There's a lot. I mean, what if, I mean, it's actually kind of comforting to see this because like even with 100 nodes, we have 1, 2, 3, 4, 5, 6, 7 levels. Not too bad. If we were to change the degrees to like 60, some weird number, size should still be the same, but it's going to be a little bit different. You can see that we basically just have 3 leaf nodes now because our degree is 60, meaning that we can fit at least 59 keys in any one of these, and they all have to retain at least half full. So even if this one dipped a little bit below half, it will borrow from its sibling. I guess I do reverse those nodes. I don't know. I'll have to think about that later. But yeah, that works. I like it. All right. So I don't need that anymore. So size works. That's good to know. So let's get back to this. Get all. Change that, change that. Let's see what else we got. So size works. The next issue is get. Oh boy. This get is basically the same as searching for a specific key with a start and end, but I really don't want to do that. Should I implement a get? And since I already have the key, I don't need to worry about returning a tuple. So let me just return a value of get, passing at the key. Return root dot get. I am not entirely sure why Xfinity is calling me. Yeah, that's not annoying. It's an 888 number, so it's probably just spam anyways. I have no idea why Xfinity would be calling me. All right, so get. That is get keys. But that is the other keys for the current node. I'm gonna have to I need to identify the other ones that are intended to be the tree as a global entity versus methods that are intended to be for this node in isolation. Because like get keys, for example, it's not going to return all of the keys across that branch, including all the other children. It's only for that one node. So yeah, you can see that it's only returning the keys and not going across the other children to get their keys. So public value get a key. This is abstract. So public v get K key. Get the location for that key, and then return children get at that location get. And then the leaf node, we need to return. This is going to be the location equals get location of that key. If the location is less than the key count. Sorry about that. And keys get at location is equal to the key. Return values get location. Otherwise, return null. All right. Yeah, that's going to cause a problem. I was needing the other previous value there. Actually, on the B tree, whenever I call add, where's my add method? There it is. It's returning void. So I could just return the previous value, right? I mean, nothing's preventing me from doing that. I can get the other key, turn the other previous value, and that's good. Kind of like the name put instead. All right, so that returns. So this returns Boolean. I should wonder if I should maybe I should change this to B. So basically the same sort of thing. Previous value equals root get key. Actually, I don't even need to do the other root, right? And just call get. Does that kill some of my tests? I'm not sure if I was checking the other return. Doesn't look like it. All right. Oh, that makes everything clean now. Let me just rerun this again. Yeah, I don't like the add method. I can have a completely different API on the B tree versus the nodes that it holds. Because I'm not actually exposing the other nodes outside of the other B tree. It's all internal. So I could basically implement the other map interface if I wanted to. Or it can create a map implementation that has a bee tree, basically like a decorator, a map decorator. All right, so that works. I don't know if this works or not, but there's no errors in my object strategy. All right, so I should be able to run this now. Well, let's go ahead and start up Tomcat. My closed captions are very weird. I said, let's start up Tomcat, and it thought that I said, what's garden art of Tomcats? That's very odd. Do you think I have a Missouri accent? I don't think I do. I know that my oldest daughter does. She has, I don't know where she got that, because I don't think me or her mother have a country twang. Yeah, it's probably very generic. I just know that I have spoken with people in the past, and they were surprised that I was in Missouri. I guess they were expecting a specific type of accent. I don't know, like hillbilly. Nope, that's just the rest of my family. There it is. Like, where is my Gwit? Both? I try not to pronounce it with an L in there. I know that a lot of people will say both. I try not to do that. I also try to pronounce egg as an egg instead of egg. Leg instead of leg. I have made conscious efforts to not sound Midwestern. Oh, that is the wrong port. Oh, yeah, my wife has too. Jail. I don't know. Gel. Going to jail. I think I pronounce that with the A sound. Mainly because of the AI in it. Jail. Probably helps also that I've been trying to learn French for the last couple of years. Why am I getting an index out of bounds? Yeah, I'm getting an index out of bounds for some reason. I haven't actually. How do I keep doing that? 9876. Yeah, one of my previous brother-in-laws, he was actually going to school for being a radio DJ. I know that they had to do a lot of activities, little exercises for word pronunciations. All right, so this is compiling. I don't know why I was getting a index out of bounds exception earlier. I'll just have to see where that's happening. And I'll need to reproduce that index out of bounds exception in my unit test so that I can make sure that it gets fixed. Let's get rid of all of our breakpoints because I don't know what we were testing at that time. Move all breakpoints. Not yet implemented. That's weird. Here's my index out of bounds exceptions. What's my call stack here? This is on get first leaf. Oh, it's because I may not have anything yet. So this is a leaf node. So I guess there's a possibility of calling get first leaf whenever there's nothing. So get first leaf node. If keys is empty, return null. Otherwise, return the first index. And in that particular case, if keys is empty, return null. So I should probably test it. And then the only way that would happen, I should have tested that before. Let me comment that out real quick. Need to get into the habit of testing first. All right. So this is only because it's an empty tree. All right, so let's go ahead and execute that. And that should fail with an index out of bounds exception. There we go. Let's go ahead and I don't know what this would do. Okay, that works. All right, so back to what I was doing. I should be able to refresh this. I can stop pausing on exceptions. Yeah, we're not yet implemented for the find, which is perfectly fine. I knew that I hadn't implemented that yet, because that was what we were planning on doing. All right, so now let's take a look at our indexes. So I am going to actually close everything out and start from scratch. So for my main entry point, so the indexes are going to be a little bit different. All right, so this is creating an index on the first name. That's perfectly fine. And let's go ahead and create another index. First name and age. All right. And let's go ahead and see what these indexes look like. Because this is going to require quite a bit of changes, because this is the old B tree and we've changed that to a new B tree. And the other keys are going to be a little bit different. So I've been thinking about this in regards to how the index can actually work. And I think it might be with a single value index. It's going to be fairly simple. It's going to have a single node for the key, which is going to be whatever the data type is for the that field, and then it's going to hold a collection, I suppose. I mean, that makes the most sense, because that way I can support multiple values on a on each one of these. Because if the value, if the key is already in the B tree, I don't want it to just overwrite what's there. I want to have all of the values for that one particular key. So first thing that I need to do is import the other B tree, which is the B plus tree. And I'm not sure what I'm holding onto. I don't think we're doing named fields anymore. So I'm adding fields. Oh, I guess those are the name fields. Yeah, I am. We're just not holding on to the function anymore, the accessor. Fine. Probably don't need that yet. Should probably just delete anything that I'm not using. All right, so whenever we are adding a doc to the current, this is where it's going to get complicated. And here I need the default degrees. And for now, increase this. We're just going to say 5 for the time being, just for testing purposes. All right, so that creates the new B tree, right? What is the object in this particular case? It's a JS object. Yeah, I might keep the key this way, even if it only contains a single value. So I guess this is going to be JS object. Not necessarily. This is where it gets a little bit more complicated because of the fact that we might have B trees with values as B trees. But for the first time, let's just implement it with a single field. So this will allow us to do the first name field, and that's going to index from first name actually to a list of JS object, right? Because we can't assume that there's only one Bob in our database. There's going to be multiple Bobs, and we need to have access to all of those Bobs in this collection. And then in that particular case, should we be holding it based upon the ID to make sure that they're ordered? Probably. Yeah, it's going to get complicated real fast because this is going to basically nest B trees together. Because before I was creating a composite key, and that's fine for like equal comparisons or maybe less than or greater than on multiple fields. That way, if you have the first name and age as a complex composite key, I'm only able to do ranges of that combination, first name and age, to another first name and age, and that doesn't make a lot of sense. For any kind of database query, we're probably going to say, give me all of the records where the first name is Bob, but the age is less than 30. So in that particular case, we're going to have a different kind of collection for that. Which that will increase the methods that we're going to have on the B tree. We just need to figure out what those are. We could probably just return all records that are less than something. That might work. It's going to be multiple B trees. I don't know what you mean by that. Like, why is that true? Like, qualify that. For example, name is Bob. We can get that list easily as Bob, Boba, basically. Right, and I still need to, right now, that one's going to be a little bit harder. I'm going to have to create a special type of comparator for that that can handle like contains. Whenever I get into like the like matches, that one's going to be a little bit more difficult. Right now I'm just dealing with like the equals and less than. Yeah, that's exactly what I said. Well, I was thinking in regards to it's got to be multi-dimensional B trees. So imagine I have a B tree. So a two-dimensional first name. I'm just going to put all of these in comments. So let's say that we have a first name and an age as our complex key. So the top B tree is going to be a sort of like this, right? So we would first search for Bob in the original B tree, and then it's going to contain a B tree. I think you don't need to get too complex or interesting here. Right, but I can't do complex keys in this particular case. It would have to be a B tree for every single one of these fields. Yeah, but then how would you... You can't change the comparator. It can't be like a live comparator, a reconfigurable comparator, because the entire B tree is ordered a specific way. So I just don't know how you would create a search for that otherwise. Right. Correct. Correct. And that makes the most sense. That's why I'm going to have something in the index to say, hey, can you handle this particular search? Because whenever we do a search down here, yeah, so we're going to have a selector that's going to have our criteria. This one, you can either specify a specific index, or it can go through the indexes. So if I have age greater than 18 and the first name Justin, it will try to find the index that matches the fields, and order does matter, because it's going to check all of these in the same order as the index to see, hey, is this selector matching this index? If so, then use that index. Otherwise, I can specify which index that I want to use. So walk me through that, because I don't see how that I couldn't find. I was doing a lot of searches and I couldn't find a lot of information on complex keys for B trees. Because if I wanted to do first name Bob and anything less than 30 for the age, if my complex key is sorting by first name first and then age second, right? I'm just trying to wrap my head around some of that. Yeah, and I haven't really thought in terms of a planner for this. I know that different database things, even if I go over to the CouchDB, not that one, this one. I think it has a planner in here. Query planner looks at the selection, finds the index with the closest match to operators. and fields used in the query. There are 2 or more JSON type indexes that match. The index with the smallest number of fields is the index preferred. There are still 2 or more candidate indexes. The index with the first alphabetical name is chosen. See, and that's where I'm trying to figure out is how to do the indexes in such a way that I can easily find this stuff. So first compare names backwards. Why backwards? Are you thinking of a, what is your query? Oh, first name descending, age ascending. Let's take a look at the indexes. See, a lot of this made sense in my head. Right. Just trying to think of how that could to function. I mean, would I have a B tree on each field that we're indexing? I just don't know how that would help. Because we need the subsequent indexes to be faster based upon the previous B tree search, right? Right. Indexes are expensive. And the more indexes that you have on this, it's going to be cutting the time, because right now I'm just running this in the same thread. So the performance, you'll probably not want to have too many indexes on your data. Yeah, I'm going to have to think about that. I just don't know. So, like I said, I've been doing some searches for this stuff, and I can't seem to find a lot of information on how to use the B trees or selectors that way. Because we need to be able to do a selector where we're doing like ands and ors and stuff like that. So I don't know. So each B tree has the key mapped to the row itself, perhaps via proxy, the row index. And if you have A and B or C, you can run each of those ABC queries on the respective indexes. Right. So in the particular case of first name and age, if I create a index for first name and age, I just don't know how I can do that easily. Not yet. I'm just trying to do a simple search for it right now. I don't care about the order at this point. Eventually I'll probably have to figure out an order. Go queries. Yeah, see with this one, it has like name and age, and you put the operator in there, and that's essentially what I was doing. I just don't know how to use the index in a way that provides a better performance. Because it's like, I need to have something such that whenever I search for, I mean, let's say that I have a different B tree on each field, I would need to be able to search the first B tree for the first name. And right now I'm just thinking in terms of equals comparison. I'm not thinking in terms of less than, greater than, or like comparison. But then it would return a collection, but then it would have to be further, because this would be an and, it would have to be further filtered by this one. I mean, sure, it could be with the intersection. Just not sure if that's the way I want to go. Because let's say that I have a million records in my database, and I choose a first name, right? So the intersection is cheaper to do without further filtering, since it can get ranges cheaply. Yeah, I can get ranges pretty cheap in the B tree stuff. Yeah, I should probably implement the full scan first. And then do something different. Yeah. Yeah, I'm gonna have to think about that. It is 2 hours into the other stream. Can't reverse the and order A and B not equal to B and A. Yeah, that was confusing, but I get what you're saying. Just trying to think of an optimized way around this, though. A might check for null, B might reference the null. Right. I just don't want to get into a weird scenario where I have a single index on the first value. Yeah, that's going to cause some problems with the ors, though. I mean, it's fine with ands because it can be like further filtering, but the ors is what's throwing me off. So it just sounds like I need a B tree for each one of these. And then based upon the outermost filter, I just don't know. So you can think about and ask your index about cardinality here. Will I get more results for A or for B? Decide about a full table scan for the other. Yeah, that's going to be hard to tell. Unless I put a lot of extra metadata into my indexes whenever I'm indexing. Well, it does look like I'm going to need to do a little bit more discovery. To figure out what the best approach for this is going to be. Rather than doing that on stream and any of the other VODs for later, I'm probably going to call the other stream now. I might come back later this afternoon or on Thursday. I do need to figure out the next step for this in regards to how to structure the index in a way that makes more sense. So yeah, let me go ahead and end it for now. Might be back later this afternoon or in a couple of days. It depends on if Colin's going to be streaming tomorrow or not. And then we will go from there. So I hope that you enjoyed today's stream. We will come back soon and try to figure all this stuff out. Thanks a lot. Bye.